History of Life on Earth. Chapter 1, Chemical Origins. From cosmic dust to the first biomolecules. 1.1 The world before the first ancestor. Every living thing you have ever seen is a distant cousin. Followed the branching family tree of life backward far enough. Past humans, past fish, past the first cells that could pinch themselves in two, and every branch converges on a single ancestor that was barely alive at all. Go back a little further, and there is no tree. There is only a planet and chemistry and time. That is where this book begins. Not with a creature, but with the conditions that made creatures possible. With ordinary matter, the same carbon and hydrogen and oxygen found in rock and air and rain, assembling itself, one chemical step at a time, into something that could copy itself and keep going. No single step in that story requires a miracle. That may be the most astonishing part of it. 1.2 Hell and what it delivered. About 4.6 billion years ago, Earth gathered itself out of a swirling disk of dust and gas, orbiting a brand new star. What formed was not a world you could stand on. Geologists call this first stretch of our planet's history the Hadean, after Hades, and the name is not poetic exaggeration. The surface was molten or half molten. Volcanoes were everywhere, and the sky kept falling. For hundreds of millions of years, asteroids and comets slammed into the young planet. And yet, here is the first of many places where the story turns upside down. The violence was productive. Those cosmic invaders brought carbon compounds and supplemented our water supply. But much of Earth's water was likely already inside the planet, locked in the interior rocks since its birth. As the volcanoes outgassed this trapped water vapor and the planet slowly bled its heat into space, the surface hardened into crust, the steam-choked sky cooled, and it began to rain. It rained, and the oceans filled. How early? Earlier than anyone once dared guess. In the hills of Western Australia, there are grains of the mineral zircon, tiny, tough, nearly indestructible crystals that are about 4.4 billion years old, older than any surviving rock on Earth. Their chemistry hints that they formed in the presence of liquid water, which would mean the hellish young planet had oceans within roughly 200 million years of its birth. Hell, it turns out, was wet. 1.3 The air we got wrong. To know what chemistry was possible, you have to know what was in the sky. Ingredients determine the recipe. For most of the 20th century, the assumed answer was a reducing atmosphere, thick with methane, ammonia, hydrogen, and water vapor. Reducing means electron-rich, an atmosphere eager to hand electrons away, which is exactly what you want if you're trying to build complicated carbon molecules out of simple ones. Today, most geochemists have revised that picture. The early atmosphere as a whole was probably only weakly reducing or chemically neutral, mostly carbon dioxide, nitrogen, and water vapor. That is a stingier chemistry. It makes building organic molecules harder. But a planet is not one place. Around volcanic vents, plumes of hydrogen and hydrogen sulfide would have created local pockets, where the old, generous, electron-rich chemistry still ran. The early Earth was not a single laboratory. It was millions of them, each running its own experiments, side by side. Keep that revision in mind. It is about to complicate the most famous experiment in the entire field. 1.42 Deliveries. Where did life's raw ingredients come from? There are two answers, and they are not rivals. They are partners. The first is that Earth made its own. Given simple and organic starting materials and a source of energy, lightning, volcanic heat, ultraviolet light pouring down from a young sun, through a sky with no protective ozone, organic molecules can be built from scratch, in place. Chemists call this endogenous synthesis. The second answer is that the molecules arrived by mail. Space, it turns out, is a surprisingly capable organic chemist. In the cold dark of molecular clouds, on the surfaces of asteroids, in the disks of dust that surround forming stars, carbon compounds assemble and accumulate. And we are not guessing about this because we have the samples. In 1969, a meteorite broke apart over the town of Murchison in Australia and scattered its fragments across the countryside. Inside those fragments, amino acids, dozens upon dozens of them, most of which no living thing on Earth uses. Also nucleobases, the letters of the genetic alphabet. Also sugar derivatives. That is not a hypothesis. That is a rock you can hold in your hand. One more detail from Murchison, which will matter greatly in a few pages. Its amino acids are not perfectly balanced. They lean very slightly to the left. So the young Earth most likely started with a mixed inventory. Some of it inherited from space, some of it cooked at home, and then local geology went to work on the pile. 1.5 The spark in the flask. In 1953, at the University of Chicago, a 23-year-old graduate student named Stanley Miller decided to stop arguing about the early Earth and simply build one. With his advisor, the chemist Miller-Urey, he assembled a small glass world. A flask of water stood in for the ocean, gently boiled to send up vapor. Above it sat an atmosphere of methane, ammonia, and hydrogen, the reducing sky, as everyone then imagined it. 2 electrodes threw sparks across that atmosphere. Lightning. A condenser cooled the vapor and rained it back down into the sea. He sealed the loop and let it run. Within a day, the water had turned pink. Within a week, it was a deep reddish brown. When Miller analyzed the sludge, he found amino acids glycine, alanine, and others, the building blocks of every protein in every organism alive. He also found a mess of other organic compounds. He had not made life. He had made life's raw materials out of nothing but air, water, and electricity in less than a week in a room in Chicago. It remains one of the quietly staggering results in the history of science. And the reason is not the amino acids themselves. It is the ease. The building blocks of biology are not rare, not delicate, not improbable. Under the right conditions, they are close to inevitable. Then came the complication. Miller's sky was, in all likelihood, the wrong sky, the strongly reducing atmosphere that geochemists have since revised away. Rerun his experiment with a more realistic, weakly reducing gas mixture, and you still get amino acids, but fewer of them and less variety. Add the conditions of a volcanic eruption, though. Throw in hydrogen sulfide, simulate the reducing plume of a vent, and the yields climb back up. Miller's result survives. It just relocates. The chemistry works, but it may have worked in particular places rather than everywhere at once. At the volcanoes, in the pockets, along the ragged edges of a restless world. 1.6 The Other Cradle. Charles Darwin once mused, in a private letter, about life beginning in some warm little pond. It is a lovely image, and for a century it was the default. But another school of thought takes the whole story and drops it 3 kilometers to the bottom of the sea. Picture an alkaline hydrothermal vent. Not the scalding black smokers you may have seen in documentaries, but something gentler. Pale chimneys of carbonate mineral, warm rather than searing, riddled through with countless tiny pores like a mineral sponge. A real place, the Lost City Field, in the middle of the Atlantic, looks like this today. Seawater seeps down into the ocean crust, reacts with the rock, and comes flowing back out alkaline and loaded with hydrogen. In the early oceans, it would have met seawater that was acidic and rich in dissolved carbon dioxide. That meeting offers 3 gifts that a lightning-struck pond cannot. The first is a battery. Across the thin mineral walls separating one pore from the next, protons pile up on one side and not the other, acidic outside, alkaline inside. That difference is a proton gradient, and here is where the hair on your arms should stand up. Every living cell on Earth, from a pond bacterium to the neurons reading the sentence, makes its energy by pumping protons across a membrane and letting them rush back through a molecular turbine. Life's central power system is a proton gradient across a membrane. The vents had one already, free of charge, before anything was alive to use it. Acidic ocean protons would naturally force their way through the leaky mineral walls into the alkaline interior, providing a driving force that early life could harness, long before it evolved its own complex metabolic pumps. The second gift is catalysts, built directly into the walls. Vent minerals are rich in iron, nickel, and sulfur, and iron-sulfur compounds happen to be very good at coaxing stubborn carbon dioxide into reacting. And once again, the evidence is inside you. Many of the oldest, most essential enzymes in metabolism still carry small clusters of iron and sulfur at their working core, chemical twins of those vent minerals wrapped in protein, still doing the job 4 billion years later. The third gift is endurance. A lightning strike is a moment. A vent is a machine, running without pause for tens of thousands of years, a permanent chemical imbalance, and therefore a permanent supply of energy. Running alongside all this is a line of work led by the chemist John Sutherland, which starts from ingredients simpler still. Hydrogen cyanide and hydrogen sulfide stirred by ultraviolet light with metal ions dissolved in the water. From that single chemical network, his group has produced the precursors of amino acids, of nucleotides, and of the fatty molecules that make membranes. Not three separate origins for the three great families of biological molecules. One network, branching. Not three miracles. One chemistry. 1.7 The trouble with water. Now the twist that makes this whole problem genuinely hard. Monomers are not enough. Life is not made of building blocks, it is made of chains. Amino acids linked into proteins. Nucleotides linked into RNA and DNA. And the reaction that links them is a condensation reaction. You join two units together and squeeze out a molecule of water. Try that in the ocean and the ocean pushes back. The reaction runs both ways, and when water is everywhere, the balance tips toward the reverse. Chains come apart faster than they form. Building a polymer in the sea is like trying to glue two sheets of paper together underwater or towel yourself dry in a rainstorm. So life is made of chains that must be assembled in the very solvent most eager to take them apart. How? There are three good answers, and they may all be right at once. The first is rhythm. On the rim of a tidal pool or the edge of a hot spring, water arrives and evaporates, arrives and evaporates. Each drying phase crowds the monomers together and pulls the water out of the way, letting bonds form. Each flooding phase redissolves the products and mixes them back into the pool. In the laboratory, this wet-dry cycling builds chains readily. The tides and the geysers may have been life's first assembly line. The second answer is a workbench. Certain mineral surfaces, especially the layered clay called montmorillonite, attract organic monomers, hold them still, stack them close, and catalyze the links between them. A speck of clay is a bench vise for molecules. The third answer is to prime the pieces in advance. Some chemistry produces monomers in an activated form, carrying an attached phosphate group, or a sulfur-based bond called a thiester, which stores enough energy that joining becomes favorable, even while surrounded by water. The thiester idea is a provocative one. The sulfur-carbon bond may have been life's original energy currency, older even than ATP, and you still run on it. Coenzyme A, sitting at the crossroads of your metabolism right now, does its job by forming thiesters. 1.8 A world of left hands. Hold both hands out in front of you, palms down. They are mirror images, and no matter how you turn them, one will never lie perfectly on top of the other. Chemists borrowed the Greek word for hand and called this property chirality. Most of life's core molecules are handed. Amino acids come in left-handed and right-handed versions. So do sugars. And here is a strange foundational rule. Every single protein synthesized by a ribosome on Earth, whether inside a bacterium, a redwood, a whale, or you, is built exclusively from left-handed amino acids, while every strand of DNA and RNA is built on right-handed sugars. Biologists call this uniformity homochirality. This doesn't mean life completely shuns the right hand. In fact, nearly all bacteria interweave right-handed amino acids into their protective cell walls. They use them like strategic structural flaws to throw off predators, acting as armor plating so host enzymes, which are only evolved to cut left-handed chains, cannot easily break the wall down. Chemistry does not do this. Make amino acids the abiotic way in Miller's Flask, in a meteorite, anywhere without life, and you get a perfectly even 50-50 mixture of both hands. So why is life so lopsided? Because it has no choice. A protein folds into a precise three-dimensional shape, and shape is everything. A molecule with randomly alternating handedness folds into nothing useful, like a spiral staircase whose steps keep reversing direction. To fold, you must be consistent. So something very early broke the symmetry. Maybe it was minerals. The faces of certain crystals grip one hand more tightly than the other, quietly sorting them. Maybe it was starlight. Circularly polarized ultraviolet light, which really does bathe the regions where stars are born, destroys one mirror, forms slightly faster than its twin, and remember Murchison, whose amino acids arrive from space already leaning left. Or maybe a whisper was enough, because some reactions are autocatalytic. They produce a product that speeds up its own formation. Hence such a reaction or nearly even mixture with the faintest imbalance, and it will amplify that imbalance, running away toward one hand and never looking back. Chemists have watched exactly this happen in the laboratory, in what is known as the Soey reaction, although in strictly non-biological conditions. A whisper amplified into a shout. Of everything in this chapter, chirality remains among the least settled questions, a fingerprint left at the scene by a suspect we have not identified. 1.9, the molecule that could do both jobs. Now the deepest puzzle of all, a chicken and egg problem written in molecules. In every cell alive today, information and action are divided between two kinds of molecule. DNA holds the instructions, but can do nothing on its own. It cannot so much as copy itself without a crew of proteins to do the work. Proteins do everything. They cut, build, carry, catalyze, but they cannot store information or reproduce themselves. Their sequences must be read out of DNA. DNA needs proteins, proteins need DNA. Neither can come first. In the 1960s, Carl Weiss, Francis Crick, and Leslie Orgel, EEC, arrived at the same escape route. Neither did. What came first was something that could do both jobs at once. RNA is that molecule. It carries information exactly the way DNA does, in a sequence of paired bases. But unlike DNA, a strand of RNA also folds up into an intricate three-dimensional shape, and shape is what makes a catalyst. For years, this remained a suspicion. Then, in the 1980s, Thomas Cech and Sidney Altman found RNA molecules inside living cells that catalyze chemical reactions entirely on their own, with no protein help at all. They named them ribozymes. RNA could be the message and the machine. The chicken and the egg turned out to be the same animal. This is the RNA World Hypothesis, an era in which RNA both carried heredity and performed the chemistry of life. And the evidence for it is written inside your own body. Consider the ribosome, the machine that builds every protein in every cell of every organism on Earth. It is made of RNA and protein together. But when its structure was finally solved, atom by atom, the site where the actual peptide bond is forged, the business end, the place where the work happens, is catalyzed by RNA, with no protein side chains contributing to the chemical reaction. It is a ribozyme, the single most important reaction in biology, carried out inside a protein factory, is catalyzed by RNA. That is a fossil, as surely as a trilobite in shale. Nothing that ancient would be built that way unless RNA got there first. Consider ATP, the energy currency spent by every living thing. It is a ribonucleotide, an RNA letter, with extra phosphates bolted on. A curious choice, unless RNA was in charge when metabolism was being invented. Consider the essential helper molecules of metabolism, NAD, FAD, coenzyme A, each of which has a chunk of nucleotide buried inside it, like Roman columns reused in the walls of a medieval church. One caution though, almost no one believes RNA was the first thing. RNA is a complicated molecule, and making it from scratch is hard. Most researchers suspect that simpler informational or metabolic systems came before, and that RNA was simply the first replicator good enough to take over the world. And once it did, it delegated. DNA, whose sugar has one less oxygen atom, making it tougher and more chemically stable, took over the archive. Proteins, built from 20 different amino acids instead of 4 bases, took over the catalysis, offering a versatility RNA could never match. RNA was left with the middle job, carrying messages between the two, which it still does every second in every cell of your body. The old king became the courier. 1.10, a bag to put it in. One thing is still missing, and without it, none of the rest matters. A self-copying molecule adrift in the open ocean has a fatal problem. Whatever it makes floats away. Its handiwork drifts off to benefit strangers. Any molecular parasite that copies faster gets the same free ride at no cost. Without a boundary there is no individual, and without an individual there is nothing for natural selection to select. Life needed a bag. Here the universe simply cooperates. Certain molecules, fatty acids and other simple lipids, are two-faced. One end loves water, the other end can't stand it. Drop them into water and they cannot be comfortable alone. So they solve the problem collectively. They crowd together, tucking their water-hating tails inward, turning their water-loving heads outward. They form sheets 2 molecules thick, tail to tail, and the sheets curl and close into hollow spheres. No machinery, no instructions, no genes, no energy source, no help. Just molecules arranging themselves to be less uncomfortable. Membranes assemble themselves. That is not a metaphor for a cell's boundary. It is the evolutionary blueprint for it. The same basic double-layered architecture that encloses your cells today. Though modern life has since upgraded from these simple, leaky fatty acids to tougher, complex phospholipids. And these simple bubbles do more than merely exist. In experiments run by Jack Szostak and others, plain fatty acid vesicles have been shown to grow, absorbing more fatty acids out of the surrounding water. They divide when gently jostled, pinching into daughter vesicles, with no proteins and no genetic instructions of any kind. And their walls are leaky in precisely the most interesting way. Small molecules like nucleotides can slip in through the membrane, while long RNA chains inside are too large to slip back out. Read that again. A vesicle can feed on the raw materials of RNA, and keep the RNA it makes. There is one more result, and it is the one that ought to keep you up at night. In the laboratory, vesicles carrying more RNA inside swell slightly with the extra pressure, and swollen vesicles pull membrane molecules away from their slacker neighbors, growing at their expense. Bags of chemicals competing. No genes, no enzymes, no life. And something that looks unmistakably like the beginning of selection. A vesicle with a self-replicating RNA molecule inside it is a protocell. A thing with heredity, with chemistry, and with reproduction. It is not a cell, but it is a unit, something the world can choose between. And once the world can choose between things, everything else in this book follows. 1.11 The threshold. By somewhere between 4.4 and 3.8 billion years ago, the pieces were plausibly all in place. Organic molecules delivered from the sky, brewed in volcanic air, and cooked in the pores of the seafloor. Clay and tide and thiester to string them into chains. RNA to hold information and act upon it. Membranes drawing the first line in the universe, between inside and outside. Notice what this story never required. No miracle. No impossible leap. No single event so improbable that we have to look away and change the subject. Every step described in this chapter is chemistry doing what chemistry does, and some of them have now been demonstrated in a laboratory. What we cannot yet do is assemble them. That is the great unfinished work of origin of life research. Not any individual step, but the integration. How these separate, well-understood processes came together, in one place, at one time, into a single chemical system that fed itself, copied itself, and made small mistakes while copying. That last part is not a footnote. That is the whole trick. Copying with mistakes is the hinge on which this entire book swings, because from that moment forward, the arrangements of matter that happen to copy themselves a little better become more common, and the ones that don't. That is the dawn of selection, and it does not require a fully formed cell in order to begin. It requires only imperfectly copying chemical systems, competing for a limited supply of raw materials. Somewhere on that young, battered, rain-drenched planet, in a warm pool, on a shelf of clay, in the dark pores of a mineral chimney a mile beneath the waves, that threshold was crossed. Chemistry became heredity. Nothing on Earth has been the same since. In Chapter 2, the bags of chemicals become cells.